Good afternoon, everyone. My topic it's very orthogonal to the previous one. I'm interested mostly in physical intelligence and mostly how physical intelligence can emerge from principles of information processing, optimal control in dynamical systems. And first of all, I will do some overview of what we know about intrinsic motivation, about emergence of purposeful behavior in dynamical systems. I show you our recent progress, open questions. And but first of all, I would like to start from motivation. Think about in reinforcement learning. The key concept in reinforcement learning would be reward function. We cannot do anything without reward function. In optimal control, we need to define cost. And think about the definition of optimal control. It's optimal up to your subjective choice of cost function. If you will choose better, you will get better solution. Exactly the same in reinforcement learning. So there are some arbitrariness in the solution in probably the most fundamental problems. Control, reinforcement learning, engineering learning. The choice of objective, it's super important because you can get just different solutions. And it's might be very difficult to choose good cost functions to complicated dynamical systems. Let's show some examples, some extreme case, super complex dynamical system, and probably a lot of engineering just to build this controller. And if this controller doesn't work, it might be a lot of even economic damage. The first part will be very short. It's case study. It's cost our economy $9.6 billion. And just zoom out and think about it. It's probably all of you know this example. It was in Middle East. It was in probably the main artery of goods transfer between East and West. It was between Egypt and Israel. It was this specific point, Suez Channel. And you can imagine that kind of probably most of the global goods they transfer through this artery. And this it's not just ships. They call it mega ships. And to control this mega ship, we need sophisticated controllers. It's many different motors, GPS navigators, and it happened already 4 years ago. Wind it caused that this 400-meter long mega ship it just blocked Suez Canal. So think about this entire system, this dynamical system, was designed by the best engineers to be stable, to follow this reference trajectory. But it looks like sometimes these dynamical systems they can lose control. They lose ability to control. Sort of controller, it's disconnected from environment, and the system can be stuck. This actually was this blockage. And again, think about it was the optimal controller with cost function chosen by humans, by engineers, and it looks like that this complicated dynamics was a little bit more difficult than human intelligence just to design. Let's do it with certain cost functions. So now the question is if it's I believe it's we need not everything depends on reward, and we need to think how we can learn properties of dynamical system, but properties that intrinsic to controllability. So that how we can discover something, how we can reveal behavior that would be controllable. And if we can characterize this scenario, this Tesla just lost the ability for control. So we have dynamical control system, and that Tesla just lost this ability to control, regardless of all these sophisticated optimal control mechanisms, because it didn't work. Second part is actually what might be a solution. We can think about intrinsic ability for control, not externally additional knowledge by human experts, by engineers. You can think about if in a perception action loop, in dynamical control system, if there's something that can suggest us how to build intrinsic control. Intrinsic ability to stay all the time in control, not to get stuck, not to get trapped, not to fall, to be in upright position stable, to get a stable configuration of ensemble of robots. And intrinsic ability to control, it's actually the goal to design AI agents that will learn to causally affect environment. By the way, there are a lot of work that we observe the same behavior in the early stages of baby development. Beautiful works by Ellis and Gopnik. And we have one principle, it's actually, I'm still an overview, empowerment principle. It can formalize the intrinsic ability for control. It's information-theoretic quantity, and Daniel actually a few days ago introduced this mentioned this quantity. It's actually mutual information between trajectories of actions and future observations. And how it can be useful? This empowerment, currently speaking specifically in continuous dynamical systems, when we can take gradients, when we can speak about continuity. We can at every state, X, it would be state of dynamical system, we can derive what would be the optimal action. And this action would be intrinsic action. It would be action in the gradient of empowerment. Sort of let's increase ability of system to be in control, not to lose control. And currently we have a lot of evidence. It can work for intrinsic control, it can work for human-robot collaboration, for object manipulation in team formations. Even some problems in AI ethics can be formulated with this principle. Yeah.
What is this gradient expression like?
Yes, good. Let's just a little bit unpack. It's kind of what you see here, left-hand side. It's information capacity of dynamical system.
So it's a kind of potential.
Yeah.
And then you do gradient descent for that.
Yeah. I calculate gradient and then sort of think about if the idea we want to be at high empowerment states from any given
gradient ascent.
Gradient ascent. Yeah. If you want to be at states with high empowerment, sort of a lot of control over environment, we want to ascend this gradient. So kind of it's tricky how to calculate this quantity because this one is mutual information of dynamical system and we take maximum over probability over trajectories and then we need to take a gradient.
And maximizing mutual information is super hard, right?
Yeah, it's super hard, and that's exactly our reason.
Maximizing a convex function.
Yeah, it's to maximize mutual information. Super hard. That exactly was a recent progress. We actually developed probably the most efficient method how to calculate this, how to estimate capacity in continuous dynamical systems, and we know how to do it in the limit of continuous time, continuous space. Sort of, we plan to build actual robots. It should be. Yeah, it was the paper. It was intrinsic motivation in dynamic control systems, and we were surprised that actually we found that its empowerment is just one representative of a very big family. And actually, in this paper, we show that there exists a unified objective. From this objective, we can derive a version of causantropic force, CF causantropic force. We introduce new quantity, control Clapeyron of exponent, and empowerment just particle instantiation. So it's an entire family of information-theoretic quantities that they characterize dynamical control system with regard to information processing between actuator and sensor. And in different settings, we get different quantities, causantropic force, exponent, and empowerment. In usually an empowerment, we demonstrate on some two examples, grid, pendulum. Now, currently we moved to use these methods to control actual robots, and we demonstrate we can control complicated dynamical system with these quantities. One work it was represented in the last ICRA conference. And for example, stochastic double pendulum. We have a double pendulum, and we can follow gradient to ascend gradient of empowerment. We can stabilize this dynamical system without any external knowledge. So without any external reward. You can try with reinforcement learning, with optimal control, try to stabilize the system, for example, with quadratic reward. It's very hard. It's hard system. Think about it. It makes sense. Think about if you pendulum this position, let's minimize this quadratic error. No, it's just wrong objective. It's wrong distance for this problem. But the intrinsic objectives, intrinsic rewards, it looks like a much more, let's say, much more. They just reflect much better the properties of dynamical system, and the learning process much better with these intrinsic rewards, and not with external, for example, quadratic reward. Okay, so far it was some sort of introduction. We have a huge limitation. All what we knew about empowerment, we knew it was open loop empowerment. So an open loop empowerment is definitely it cannot be robust. unpredictable perturbations, they will just the solution wouldn't be optimal. Just to elaborate, what does it mean? This is setting for open loop. We want to calculate empowerment of at current internal state. We have external state W, we have internal state S, and you can see that this cross arrow state doesn't affect action, state doesn't affect action, state affect only current state, and only actions will affect future state. So there are no connection between state and current action, sort of open loop. No connection between state and action.
Is it sensor and action maybe?
Yeah, you can think about kind of it can be internal representation after sensor. Yeah. Okay. Yeah, and now it's actually what I want to show. It's actually we discovered that we can do intrinsic motivation in closed loop, and we called this new formulation of empowerment process empowerment, and we discovered that intrinsic motivation can be robust. So before that work, we didn't ask this question: how much robust empowerment? Because it's not robust; it's open loop. We know unpredicted perturbation in the future. They will lead to very suboptimal solutions.
Sorry, can you go back to one slide?
Yeah.
So this is the open loop.
This is open loop just because kind of just think about schematically open loop. The only current state affects policy, but for example, next state it will not affect actions.
Oh.
So stating that it's open loop. Your current state, you pre-calculate action sequence, you apply this action sequence just as script. Okay, open loop.
Yeah.
Without interaction. This is standard empowerment. This is what we.
So the first one does, but then
yeah.
it doesn't.
Yeah, this object policy currently the first state affects policy, but then they are just you have some script and you just apply this script.
So it's not there.
Okay.
Right? Yeah.
Basically, this one underestimates what you could do if you have a lot of noise in the environment, or a lot of perturbation, or a lot of adversarial. So open loop empowerment works, kind of, but if something is going to happen in the future that you cannot account for at this stage, you may underestimate how much influence you really have over the future.
Yeah, sure. It's not if even with epsilon noise, this one would be underestimation. You can see that information in bits for any perturbation in the future. This one it would be less than closed loop empowerment.
It's like it would never tell me to drive to the grocery store because I would just like crash.
For example.
Bar every time.
Yeah, by the way, in the paper we have all this comparison between open loop, closed loop, how many bits we can lose for different noise levels. Okay. Yeah, and the idea was how we can use the same idea that we wanted to measure causal effect of agent actions on future observations, but now to do it in closed loop, not with pre-calculated scripts, but in closed loop with interaction. And we suggested this closed loop graph. Currently, you can see the difference in the previous scheme on the current state. It affects policy, but the future states they don't affect actions, don't affect anything. In closed loop, we see that now we have every state at every time it will affect action. So now policy it can adjust. If there would be a noise, there would be a unpredicted perturbation through this interaction between state and action. At every time, there would be a feedback loop. So now what we actually formulate is by a new objective. This objective it's actually objective between trajectories, all the past. It's both past actions, path trajectories. How much all this information will affect next future state, the time t plus 1. And again, we can calculate in continuous time limit as well. Okay, but now the problem becomes much harder. Much harder because now we need to calculate not a single policy, just by Blaut-Remote, by Gaussian capacity. Now we have a family of policies. Now we have actually t policies, and action at time t, it depends on all the past. Okay, and now the first question, if it's solvable, if it's if the unique solution, and first of all, if it converges, if the unique solution. In this paper, we prove that actually the unique solution, and we can formulate this problem, appears to be convex problem in the set of these policies, and we call this alternating Blaut-Remote algorithm, and we can calculate process empowerment and with this closed loop graph. So now we have just this notion robust intrinsic motivation, and not this limitation that we pre-calculate script, we apply this script, and we cannot react to unpredictable perturbation or to some stochasticities. Question about this?
Do you assume like some kind of steady state or something?
No, we don't need to assume steady state. What do you mean steady state? We calculate, in this case, it would be a capital T policies. If there would be very long trajectories, there would be some steady state. Yeah, then it will converge to some.
You don't assume it.
No.
And you don't have to like unroll the whole.
No. Okay. Now, actually, what's the difference between open loop empowerment and closed loop empowerment? Some paradigmatic example, it was example by Christoph Salge, one of the students, Daniel, and the example is what we couldn't do with open loop empowerment. We couldn't do that. Simple example, just didn't work. What's the example? Example we have, think about, we have this open loop empowerment, we have a small room, agent start at this green spot, these black blocks, they represent a narrow bridge with wind, sort of like trying to connect it to that problem, $9 billion. And then after this bridge, there are huge space with much more degrees of freedom. So think about naturally, if empowerment is about degrees of freedom, the ability to move in different directions, that intuitively, agent should try to pass this bridge and to be in this open space, because in this open space we'll have many different options where to move. It's actually a notion of empowerment. And if you remember that empowerment, we want to know where to move, what step to take. We want to be able to follow gradient of empowerment. Think about empowerment should increase from this green spot to this large room with a lot of degrees of freedom, if empowerment makes sense. But in open loop empowerment, you can see that this gradient, it will drop. Just because of this perturbation, because of this noise, we lose control in the middle of this bridge. And sort of we cannot follow, agent will not see this large room, and it will just pass this bridge. With new formulation, process empowerment, we see that we have a quite nice gradient, and the agent will, it's exactly the same noises, but now what you see in color, it's empowerment in nuts. And you can see that at every step, agent will sense that after this bridge there would be a lot of degrees of freedom. So there would be a lot of it will actually feel this it will be able to get to this state with high empowerment. Yeah, the secret sauce is because now we don't pre-calculate action sequences. Now we do it with feedback. So that there would be noise, we'll know how to adapt. Okay. That actually was proof the concept that open loop empowerment it's indeed it has limitations. And think about empowerment, it's about agent will try to be in, for example, in the center of the room. But now we want agent that will pass a narrow bridge with wind. And sort of there's some contradiction. It's not contradiction to a principle, but contradiction to open loop. But now we see that empowerment with closed loop. It works, and we can hopefully solve these problems with complicated machine, and so it can. But it appears that we can use empowerment for, now we can use empowerment, this closed loop empowerment, for very different purposes. For example, we can take a deterministic solution. For example, you can pre-calculate solution by reinforcement learning, optimal control. You can pre-calculate deterministic solution, and then you can try to run this policy, pre-calculated policy, in an environment with noises. And definitely deterministic policy, if it's not trained in stochastic environment, wouldn't be optimal. The question is if we can, in an optimal way, sort of to robustify, to take oracle solution, to take existing solution in calculated in environment without noise, and use it in noisy environment. And how we can do that? We can take oracle solution, and we can create sort of empowerment cushioning. We can create sort of additional actions that will still keep oracle policy optimal, but they would be robust to noises. In this, this what you see here, it's we call the trace scenario. We have this white states. It's actually about it some racetrack. These blue arrows, it's oracle actions or some pre-calculated given actions. At every state we have some randomness, some noise, and with open loop empowerment, we see that agent can follow oracle when there is no noise. This alpha parameter is for noise, but when we increase a little bit noise, the stochasticity is a little bit larger, that agent just gets stuck, it will fall off this track and it cannot continue. With process empowerment, it's very robust, it can work without noise, with noise. So kind of why it's significant, we take pre-calculated policy, oracle policy, controller, pre-calculated in dynamics, without noise, without any stochasticity. We mix this deterministic policy with empowerment policy, and we get a robust controller in an environment with noises. So it's actually, think about why it might be useful. It might be useful. Usually, it might be simpler to calculate a policy, deterministic policy, and deterministic dynamics without noises, and then just to add this empowerment cushioning if you want to run this policy in dynamics with noises, with stochasticity. Yeah, that actually was main progress. Now we have this, first of all, this notion of robust intrinsic motivation. We see additional properties of closed loop empowerment. How we can robustify deterministic policies to stochastic environment, yeah. Beyond today's talk, it's we apply principles of collective intrinsic motivation in artificial agents, and currently we think about how to study natural ant colonies with these principles. Emergence of purposeful collective action in ensembles of selfish actors. Questions how we can factorize intrinsic and extrinsic elements in complex behavior. For example, in locomotion, some part it would be intrinsic, some it would be extrinsic. Object manipulation, how we can do factorization, collaboration. And all this we are trying to do is to understand, to develop physical intelligence, and how physical intelligence can emerge from, I wouldn't say first principles, but from principles of information processing and optimal control. Any questions? Yeah, go ahead.
I didn't quite understand. Does the deterministic policy, does it make it easier to calculate the process empowerment, or
no?
Why don't you just, like, if you can calculate the process empowerment with noise, why don't you just?
Think about process empowerment. Empowerment, it's local quantity. Think about you calculate oracle, it will give you this flow. just think about it, would be a flow to run on this track. And now you want locally, it will follow this flow, but it wouldn't be affected by this stochasticity, by these random noises. So empowerment will not give you
it won't do anything.
Yeah, it's kind of empowerment itself. Empowerment itself is just local.
Because empowerment just wants to theoretically be able to do everything.
Yeah, in addition, kind of it's local quantity. There wouldn't be global pattern that it will create some global motion.
Okay.
Yeah.
Can you go back to the process empowerment? Yeah, I have two questions. First, so you added that the mutual information should be also with the sensors from 1 to t from time. Like the regular empowerment objective is just st plus 1.
Yeah, that's for comparison. It would be, that would be the abuse of net. It's in regular empowerment it would be just action sequence from A to T. There wouldn't be this term. So without this term.
So why do we add that term? Because we could marginalize out the intermediate observations, or.
Why you added this term? No, what do you mean to marginalize? It would be.
You could still optimize over closed loop policies, it seems, but still have the same exact objective, right? It seems like you changed kind of two things, if I'm understanding correctly.
First of all, there wouldn't be a closed form solution. It wouldn't be convex. Yeah, sure.
That's what I suspected.
There wouldn't be, and in addition,
there is a different term that's probably a bit cleaner than this one, and we have discussed it. About that will not give you such a nice blow-dairy motor.
I see. So that's what I suspected. Yeah. So this makes it tractable, actually.
Tractable and kind of it still has all the properties of empowerment. Yeah.
But it's a different objective. I mean, you could also do like regular empowerment for that objective.
Yeah, we can do, but think about kind of what we for zero noise we have exactly the same. It would exactly the same objective. So the difference would be when you add noise. This one it would be higher.
We have to be careful. The other objective cannot be written as a mutual information. The other objective is not a mutual information. That you write a code-Leibler term where you marginalize out essentially the intermediate states, except for the averaging over the policies. So the only place where the intermediate states appear is in the expectation value over the policies.
Yeah.
But the term is not mutual information. It is essentially some kind of averaging over some kind of code-Leibler term.
I see. I guess I'm kind of like, if I look at this and I think, okay, in a way, it's like, oh, what I want to maximize is the mutual information between like all my sensors up to time t and my initial action and the next sensory state. So it's a little.
That's why we called it process empowerment. That was a deliberate decision.
Yeah.
We didn't call it feedback empowerment because where you might overestimate is that if the sensors have a bit of noise and that noise somehow affects the future, then this will be overestimating it slightly. And that's why we call it process empowerment, to make clear, be honest about that. But the other quantity is formalizable. You can write it down. You could in principle maximize it, but not with a upload or
And then I guess because you include this, you could just write out you can split the mutual information into the contributions from the I see. I see. So that's why you can solve it.
Yeah, the surprise is that we can optimize all these policies in arbitrary order.
Yeah.
And then it can be a super efficient calculation. Think about it, they can update all these policies at once in different processes. And that
you don't have
I don't need
kind
to
of couple them.
Yeah.
Yeah, or you can decouple them by doing the alternating.
Exactly. That is why kind of it's alternating blow-dairy motor. This is how we call it. Yeah.
Very cool.
So we don't need to take gradient. We don't need to do component-wise optimization for each property. We can do it once for them. It becomes sort of fixed point iteration.
That's pretty cool.
Yeah, and then kind of it's super fast. Think about kind of this number t. If you have a t processes, you can calculate everything at once. Yeah, and now we extend it to continuous system, because this one formulation is still in discrete, and we have formulation for continuous, currently we do the same experiments, but with coupled dynamical system, coupled pendulums. So it would be next work.
One example that Stas hasn't shown is where you have a completely free hallway. You have an oracle that says move right, and then he puts obstacles in there, and then with the empowerment and the oracle, it will avoid obstacles.
Yeah,
so you don't have to train it for avoiding obstacles. Just standard oracle plus process empowerment, and it goes on.
So this one is open loop. Alpha, it's noise level. If there are no noise, agent, it know if it will get to this, it will take this action, it would be trapped, which actually contradicts empowerment. There wouldn't be, it won't escape. Without noise, it can find this this path. When we increase noise level a little bit, it gets stuck. It doesn't know what to do. But with process empowerment, pretty robust. It's kind of it knows. It doesn't take this direction at all. So it knows how to correct itself. And now we have ideas how to apply this stuff to pre-training without any data, deep neural networks. But it's in a work in progress. Because it's something intrinsic. You don't need data to design what would be the optimal set of parameters for deep neural network, and it should be sort of this type of calculation.
But there's something weird about this objective, right? Like imagine your action is to go listen to the radio or go watch TV.
Okay.
The TV has way more mutual information between like sensory states over time.
Mm-hmm.
So there would be a bias to go watch TV, not because like you just go to an environment that like the sensors just carry way more information over time.
Yeah, but do they have an effect on the final state, right? Well, it only matters if you're completely right. If the sensory noise does actually leak into the final state or observation, because everything empowerment does, right? The whole philosophy of it, why we don't look at the process usually, at the trajectory empowerment. That was something that Alex Lubin suggested, and then we decided not to do. It all matters what future choices you have. How many futures can you select? So all that matters is how many effect would the TV have in the selection of the final thing. If you watch TV, you know, some reality show, and at the end of that, you decide that you're going to buy a beer that had nothing to do with a reality show. It doesn't matter that there were lots more sensors. It's completely irrelevant. So it's only relevant if that reality show actually made you buy, I don't know, I'm now buying this super energy drink, and that was a reality show. Then yes, you would completely be right. It would overestimate empowerment from this reality show.
Well, I also have a similar question, but if this agent can learn about the environment, right, then mutual information between action and the sensor input doesn't mean anything, right? So when they have the internal model of the environment, so the sensory input from the outside doesn't mean to change their action, right? So when they have a model, I mean, for example, like they have a neural network inside, then they can they can predict what's the next sensor is.
Yeah, but it's less about if we know the model, it's actually what would be the optimal input to this model. So model can be given, it can be learned, but this question kind of, it's more about if we have a model, it's more about we need just channel, we need conditional probabilities, not joint probability. So we optimize over input to this model. So it's not question of learning. It's question model can be given. It's even not to predict what would be next state or future state. It would be to predict what would be next or future state caused by actions. So it's if we have a Tour model, this probably empowerment would be less reliable.
But still, the outcome is the same, you think? I mean, even if it's a poor model or a rich model?
It would be, think about it, the question would be, if you have an exact channel, then there would be its true capacity. If you have approximated channel, there would be some lower bound to that capacity.
So model, you need model for a problem because you look into the future. And if you have a model, then this model, if it's imperfect, say it's a Bayesian model, you're learning it, if you're getting better at it, it will be noisy and therefore lower than the true empowerment of the reality. So if it's let's assume the reality has a real model that you can't distinguish, you don't know what the buttons are doing. If you have a wrong model, we have not studied that. I would expect your empowerment just as off, right? It will tell you how you have empowerment here, and you don't. And we would learn to improve the model and turn the model would be closer to reality, but we haven't studied that at all.
So I see.
I have no intuition in that.
Well, because I thought, even if you start with a wrong model, that you can, repairing the model and then go to this direction. Also, when I was studying with a bunch of agents, right, then the behavior of the mutual information between, next sensory input and present sensory input and then also the action is different, And I mean, even if the same number of group, but the behavior is going to be very different. So that I thought, maybe they have a different internal model. That's why their behavior is going to be different.
Yeah, it's really different. But we start to see some new phenomena. For example, think about it. You have a finite state space, limited state space. We have many agents, and you have one sort of big guy. It would be noise. And then think about optimal solution from perspective information theory. It would be an orthogonal solution. They shouldn't collaborate at all. But once you start to add, for example, noises, there's just not enough space to do orthogonal solutions. They become some collaboration through projection, one agent on another agent. So now we started to see that we can characterize just geometrically, characterize with, probably with first principles, when we can get collaboration, when we can get competition. Yeah, different types of behaviors will arise in a limited space, and for example, there would be only two agents and huge noise. Then we can get, for some power noise, you can get collaboration, for some you can get competition. So if there would be, in some limit, there would be a lot of small agents and there would be small noise, then again, after some density of agents, they just must collaborate. Because there's just not enough space to get full decomposition to maximize information capacity. So they try to do that, but it's not kind of they got something that would be a correlation between actions, and we call it there would be some action would be collaborated. They will try to move with some coordination. So yeah, all these questions, once we don't have even many agents, it's enough. You have dynamical space with finite dimensionality, finite power of agents, finite power of noise, and for different sets of parameters, number of agents, power of noise, we can switch system from collaboration to competition, and it's actually And currently we're trying to do it with swarms. We plan to do it with drones, just to do it. But again, this whole idea is to implement, to show that this physical intelligence can build robots. It's not just two examples here. And in many times we need to redefine all these calculations just to do it doable in real time. And now we hopefully start some collaboration with somebody to test these ideas with real ends. We explained what we plan to do, and he thought it makes sense. So now sort of kind of collaboration. Once we can get this notion, think about it, you have selfish agents, they try to maximize the same objective, but because of limitation of space, at some point of time, it's more beneficial to start to collaborate. So that's sort of this constraint, this pressure of environment, it creates collaboration. And this is exactly the kind we study with actual robotic systems. And there are a lot of questions kind of even to calculate it. In many cases we do, let's say, development, at sort of engineering level. Gaussian linear approximation, but to do it in probably we need some tools from stochastic thermodynamics to do it to calculate probably even more precisely.
Yeah, but my question is, motivation was because when you do the same experiment with the real ones, and then behavior is different because of the individuality, and then I thought they have a different internal model of the environment. Therefore, their behavior is going to be different. So that I was wondering, sometimes, after a while, then the individuality will be developed, or internal model will be, changed.
Yeah.
Right.
Yeah.
So that's this kind of complexity. If we want to understand with working with the real ones, and I was wondering what is the strategy that you are going to do? That's why.
Strategy just we first of all we probably. Just now we started to see something that we can calculate for realistic systems, not just for example with grids. And currently, even we are trying to do how we can design different types of crystals with what would this crystal with different types of interactions, and kind of for that there would be different models. One, for example, atom it would have one model. All this would be different models with different ratios. We hope to get different types of new artificial materials. And again, kind of currently I'm writing proposal on this topic, and it's for people in design of material, it makes sense, kind of that. So that once you explain, you have one agent, and it tries, to occupy some volume of state space, and this is objective. And now every atom tries to do the same, but now they're limited in your space, in energy. What kind of new material or behavior we'll get? This we will try to simulate and to build.
We should also mention that there are experiments where we do a Minecraft type scenario, and you get very different results depending on what the forward rollout of your Monte Carlo sampling get you. So you get essentially in our experiments 3 classes, in that specific experiment, 3 classes of models, if you like. And if you don't see certain solutions, they will not appear as a strategy, will not be included in the strategy. So it's completely legitimate what you're saying. I completely agree with you. If you have an individual model, which you usually have, you might get a variety of strategies. That is perfectly possible.
But what you said made me think that also, like, maybe imagine we do this optimization for 2, 3, n agents at the same time, and they have the same exact world model.
Exactly, they have the same count.
Yeah, but there's a symmetry breaking, and they do a specialization, right? That's also possible.
Exactly what we observed. Yeah.
Okay, yeah.
It's enough, for example, to increase a little bit, for example, noise power, and you see different behavior. Just we can demonstrate.
So they choose different policies.
Yeah, they choose different policies. For example, one of my students, Tristan, he will represent Daniel will have a workshop in 2 weeks, and we present. We created 2 couple pendulum. Each of them it tries to maximize its empowerment. And for small changes, for example, in initial conditions, for small changes in plane horizon, we can get totally different behaviors. One, they try to be at upper position simultaneously, so they collaborate. Once, only one in a with a little bit different setting. One tries to be at the top, but it doesn't give to the other to get to the top. So there are many different.
Interesting. But do they have to model the other agent?
We can't assume the simplest setting that it's exactly the same replica. Think about the same replica, the same model. No. They shouldn't. They even shouldn't know. We consider. Think about the two agents. The other agent, it will just exert force on the first agent, just through force. No, we don't need to know. We need to know only every agent should know its model, and it should feel force.
You can choose, right? You can choose to model the other. You can choose not to model. In this case, we don't.
No, we don't model. And if we all we need to think about
I mean, that would be really crazy if they're all optimizing their empowerment, but they're also like their role model includes the models of the other agents.
You could do that. The
You
question
could.
is, does it converge? We don't know.
Yeah.
Does it do something sensible? We don't know. So it really would, I would say, it's a whole class of problems that is open to discussion.
Yeah, and
So what does Christoph call it? Transfer empowerment? What does Christoph call his work with? Transfer empowerment and these kind of things, where you actually maximize not your own empowerment, but empowerment.
Cross empowerment. Transfer empowerment, yeah. So
yeah, in that case, we need to know.
Maximize the, like you can act so that you maximize the empowerment of some other person.
Of your boss.
Your boss.
Yeah.
Exactly. I mean, like, you can call him, then you can call him your boss.
If you, I mean, there is a paper where we have a discussion of analogy between the cross-empowerment types and the 3 laws of robotics. You can basically translate each of the laws into a form of cross-empowerment. And you can, for example, preserve yourself as law 3. This is just regular empowerment for the robot. But, for example, law 1, preserve the empowerment of the human. That means it's law 1. And that is actually solving Asimov's problem of locking people in a golden cage so they are safe. So preserve the human empowerment means give the human maximum opportunities and keep them away from death at the same time. Number 2 is kind of be available to the human for cross-empowerment, so where the human has influence on the robot. So basically you see the analogy, and there's some nice follow-up papers on that by Christoph and colleagues. Very nice ones. I recommend the ones with new and unexpected ways to be mean. That is a paper about video opponents where empowerment sign has been turned around. And you can imagine that a paper where the word supervillain appears, it might be interesting to read. I recommend that. It's good reading.
Which one?
Yeah, sure.
And unexpected ways.
So is empowerment and causal entropic forces basically the same thing?
Let's say, in the original,
I'm like very confused about this.
no, in original cause entropic force, you have small perturbation, uncontrollable perturbation. Like you have system, you introduce perturbation, and you see what will the future cone of your trajectories. And you calculate entropy, and cause entropic force will just gradient that entropy.
I see.
But now can think about, that wouldn't be the maximal achievable cone if this perturbation would be optimized. So what we call by skipped empowerment, we introduce the best perturbation to open the maximal cone. So cause entropic force is just, they're physicists. They're not.
So you kind of go to the most unstable locations.
Not unstable. You see the maximal the maximal diversity of future options. But you can do it with controllable perturbation. That would be empowerment type methods. Or you can do it just a physicist. Let's put some perturbation. This is different.
So they're closely related, but they're not the same. In this paper, by the way, if you want to understand the link, I think this paper, this PRX paper about intrinsic motivations and dynamical systems is a good starting point.